Alright, here's the Chemistry 1 video for wave theory. So, electrons can be in their ground state or excited state. Here's a couple of little definitions for you. The ground state is when your electrons are at the lowest possible energy. In other words, when your electrons, I hesitate to say, are on the lowest energy level, for reasons that we'll talk about when we get to Unit 4 and start talking about orbitals and filled energy levels, etc. But the ground state is when all electrons are at the lowest possible energy that they can possibly be at. The excited state is any time you have an electron that does absorb some energy to jump up to higher orbitals or higher energy levels. There's a joke down there at the bottom, which has more energy, a steak or a hamburger. Well, it's steak because hamburger is in its ground state, because hamburger is ground beef. Ha ha ha, jokes. Just know the ground state and excited state. Ground state is at the lowest possible energy. Excited is anything that's not the ground state. So when those electrons fall from a high energy level to a low energy level, it releases energy in the form of light. You learned that a little bit in your electron energy and light POGL that you did yesterday. But when an electron starts high and falls to a lower level, it releases the energy in the form of light, particularly a single wavelength, depending on the atom, because every atom has different energy levels. But when it falls from level 3 to 2, it's going to release a particular energy of light. When it falls from 3 to 1, it's going to release a particular energy of light. 4 to 3, etc., etc., etc. That's where the unique emission spectrums are, because every energy level is a little different for every single atom. So every time the electrons fall between different energy levels, they're going to release different energy levels of light. Therefore, different wavelengths of light, therefore different colors of light. When your electrons jump, they jump from low to high because they are absorbing energy. So when energy comes in, the electron absorbs it, and they jump up to higher energy levels. Now, we've talked a little bit about the idea of light, but we're going to really just kind of go over as much as we can. This is really a physics thing. You're going to really get into waves and parts of waves, etc. in physics, but we're going to at least kind of skirt the surface here for just a second. So waves, there's 4 main parts of a wave. The first is the wavelength. Wavelength is going to be that number 1 right there. Essentially, it is the distance from peak to peak. Okay, so from the top of the hill to the next top of the hill. It could also be from the bottom, at the very, very bottom, to the next very, very bottom. It could be from center through one up, one down to the other center. All of those would be considered the same distance. So all of those are considered wavelengths. Amplitude is the height of a wave. So amplitude. So notice the height, whether you're looking at it up or at it down, should be the same. That's what an amplitude is. Trough, that is the bottom portion. So the valleys. Crest are the proper term for the peaks, the tops. So those are the different parts of a wave. You need to have a general understanding of them, but physics is where that's really, really going to come in. Another very important part of waves that we can talk about is this idea of frequency. So the idea of frequency is essentially how many cycles can you get through in your wave for every second. So if we look at that top example, I can go through 1 cycle, 2 cycles, and there's just 1 up left. Let's kind of do some visual for you there. So 1 cycle, 2 cycle, and then another half cycle. So we would say that top wave would have a frequency of 2.5 hertz, which we'll talk about the units here in just a second. So 2.5. I know this graph is a little weird because we normally don't have something that quite looks like 0 to 1 second on the bottom, but know that we're talking about time here. How many cycles can we get through in a single second? When we look at that next example, there's 1 cycle, there's a second cycle, that would have a frequency of 2. And hopefully you might be able to start seeing this pattern at this point. There we go. We are just looking at how many wavelengths can we get through in a single second of time, literally 1 second, how many times can you go up, down, back to the start, up, down, back to the start? So we've talked about the parts of the wave, we've talked about frequency. Now let's talk about the two formulas that we're going to be using for literally every problem that we give you. You will use one or the other of these. We will give you both of them. You don't have to memorize them. But we won't give you what all the different variables mean. You do need to know those. So for that first one, let's look at the left. C equals a weird kind of upside down y, we call that lambda, times F. C stands for something called the speed of light. It is a constant. We talked about it a little bit in the POGL. It's the speed of light specifically in a vacuum. So 3 times 10 to the 8th meters per second. That's your C. Equals lambda, that little upside down y. It's a Greek letter. It's the variable to represent wavelength, and it is measured in units of meters. Okay, so when you go to physics, you'll be using these formulas again. They love giving out their wavelengths in nanometers. We will always give it to you in meters or millimeters. But when you actually do plug it in the formula, use it, you need to make sure that your wavelength is in the units of meters. Last but not least, F. F is a pretty easy one, stands for frequency. It is measured in something called hertz. So Hz is the abbreviation. The real unit of hertz is 1 over seconds, in other words, inverse seconds. But that can be a little confusing to see a lot. It can be a little confusing to see in papers. So it actually was given its own unit, hertz. That is our unit of frequency. Okay, so that's the first formula. C equals lambda times F. Now let's look at the one on the right. E equals H times F. E equals energy. That's what it stands for. It's the variable for energy. And E is always measured in units of joules. Okay, that is the designated unit of energy. H is another constant. It's Planck's constant. 6.63 times 10 to the negative 34 joules times seconds. It's just another constant. It's like C. We will give you both constants. Don't memorize them, please. We will give you that C is 3 times 10 to the 8th. We'll give you that H is 6.63 times 10 to the negative 34. Last but not least, you have frequency again. F, again, still measured in those units of hertz inverse seconds. So these are the two formulas that you have to be able to use. Don't memorize them. We will give you these formulas. You do need to know what all the variables stand for. You do need to know how to use these formulas. See, I promise, right there, given on tests. We'll give you both formulas, and we'll give you C, and we'll give you H. Don't freak out. Don't try to memorize them. They're there for you. Okay, here we can see a filled-out version of the electromagnetic spectrum. We saw it a little bit in that POGL on that 4th page. Again, we see kind of the gambit of different types of waves. We see visible light kind of right there in the center. We have radio on one end, gamma on the extreme other. You really need to understand, if you take nothing else away from this page, please understand the relationships between energy, frequency, and wavelength. You really need to get it. Okay, so over on the gamma ray end, I have very, very high energies, very, very low energies on the radio end. Okay, so that first kind of picture there shows those wavelengths. Well, as I start at the radio side, I have very, very, very high wavelengths. You see the distance from peak to peak kind of over on the left side of my spectrum, radio, microwave, infrared, etc. Very, very long waves. Because they're very long waves, we know that it has a very, very small energy. Okay, so we have an inverse relationship between wavelength and energy. Low energy means high wavelength. As we look down at the next table down, we see that as I have a very, very high wavelength, I actually have a very, very low frequency compared to everything else on that chart. Okay, 10 to the 4 is a big number, don't get me wrong, but it's way smaller than 10 to the 15, 10 to the 16, 10 to the 20. So that tells us that as my frequency is increasing, I also have, or sorry, as my wavelength is increasing, I actually have a decreasing frequency. Okay, so a low energy means a low frequency, but a high wavelength. Okay, let's flip all of that. If I have a high energy, that means I have a very small wavelength. You can see that the distance between the peaks of all these wavelengths are pretty small. Okay, so as I have a higher energy, that means I have a smaller wavelength. But again, we look at that frequency chart, 10 to the 4th versus 10 to the 20. That's a very, very high frequency. So you have to understand these relationships. Energy is low, wavelength is high. That tells us that there's an inverse relationship between energy and wavelength. You covered that in your POGL already. But now we're going to have to throw frequency into this as well. If I have a high wavelength, that means I have a low frequency. So they're also inverse. Frequency and wavelength are also inverse. If you want to compare energy to frequency, they both decrease together. If I have a low energy, that means I have a low frequency. That means they're directly related. They are directly proportional. That means they do the same thing. So know those relationships. Energy and wavelength is inverse. Energy and frequency are direct. And wavelength and frequency are inverse. So besides knowing the concept-y ideas of types of particle or types of waves and these relationships, you're also going to have to do some math with those formulas. So first problem says determine the frequency of light whose wavelength is 4.357 times 10 to the negative 7 centimeters. And that centimeters is going to be real important here in just a second. So I want to know frequency. I have wavelength. Luckily, there is a formula that relates frequency and wavelength. C equals lambda times F. C is the speed of light. It's given right there. Lambda is our wavelength, but it's specifically our wavelength in meters. So before I'm allowed to plug in that wavelength, I'm going to have to do a little bit of dimensional analysis. I'm going to have to turn my 4.357 times 10 to the negative centimeters into meters. It has to be in meters when you plug it into that problem. So I do a little bit of math, and I get that my 4.357 times 10 to the negative centimeters is 4.357 times 10 to the negative 9 meters. Okay, so now I have it in the right units. So I'm going to scroll it just to give me a little bit more space here. So now I can actually get to the work on my problem. C equals lambda times F times frequency. I'm looking for frequency, so you could plug in your numbers first and then rearrange. I like to rearrange first and then plug in my numbers. So since I'm looking for F, I want to get it by itself. I'm going to divide both sides by lambda. And I can rearrange my formula to say frequency is equal to C over lambda. I know C is 3 times 10 to the 8th meters per second. And I'm dividing by my lambda, which I found above to be 4.357 times 10 to the negative 9 meters. My meters cancel out. I end up with 1 over seconds, otherwise known as hertz. And so I get that my frequency is equal to 6.885 times 10 to the 16 hertz, or 1 over seconds. Make sure you're typing those in. Make sure you're doing your scientific notation right in your calculator. Make sure you can get to that value. All right, problem 2 says determine the wavelength in meters of light whose frequency is 3.45 times 10 to the 14 hertz. So let's think for a second. I want to know wavelength, I have frequency, and luckily I have that formula that relates frequency and wavelength. C equals lambda times F. When I plug in my frequency, it needs to be in hertz, and luckily I have hertz right here, 3.45 times 10 to the 14. So I don't have to do any dimensional analysis this time. I can go straight to my formula. And since I'm solving for wavelength, I'm actually going to rearrange so that I can get wavelength by itself. And so I get lambda is equal to C over F. All right, just divided by F on both sides. That's all I did, just pretty straightforward algebra. 3 times 10 to the 8th meters per second. Divide my frequency, which is 3.45 times 10 to the 14 hertz, or so that you can see it cancel, 1 over seconds. My 1 over seconds is going to cancel out my 1 over seconds there, and I'm going to be left with meters, which should be my length, my wavelength. And when you plug that into your calculator, you should get something on the order of 8.70 times 10 to the negative 7 meters. Again, make sure you're typing this into your calculator correctly. Make sure you can get to those answers. All right, last example problem that we're going to have right here. Determine the energy in joules of a photon whose frequency is 3.55 times 10 to the 17 hertz. I want to know energy this time. It's a little bit different. Luckily, though, I have a formula right there that can solve for energy. Energy is equal to H times F, which means I need to know H. Well, I give you H, it's right there, times F, my frequency. Oh, and hey, look, I know my frequency. So I don't have to do any fancy dimensional analysis. I can jump straight to my formula. In fact, this time, I don't even have to rearrange since I already have E by itself. So I'm going to start plugging and chugging. You'll see that a lot of these problems are really just plug and chug problems. So I have my Planck's constant, 6.63 times 10 to the negative 34 joules times seconds, times my frequency, 3.55 times 10 to the 17 hertz. Remember that hertz is really 1 over seconds. So since I'm multiplying these guys, I really have seconds over seconds. I'm going to be left with joules, which is my unit of energy. So I know I set up this math problem right because my units are going to cancel each other out. When you plug this in, you should get 2.35 times 10 to the negative 16 joules. That's it. Nothing too crazy here. We're just plugging and chugging using formulas that we will give you on the exam. Do not memorize that stuff. Just know what all the variables represent. Okay, no more math for right now, but we do need to talk about something kind of interesting called the dual nature of light. It's not the biggest thing in the world that for you to know and memorize, but it's kind of interesting when you really think about it. Light is weird. Light is very weird in the sense that we know that it actually acts as both a wave when it needs to act like a wave and a particle when it needs to act like a particle. We're, as far as I know, still not really sure why it does this, but we have proof that it does. Particles have to be conveyed through a medium. They have to have something to transfer those particles. Otherwise, it has to be able to travel as radiation. Well, radiation is a wave. It doesn't need that radiation. So when light comes to us from the sun, it travels through space where there is no medium. So we know that for light to get from the sun to Earth, it has to travel as radiation, which is great. It heats the Earth, life is good. Literally all the energy on Earth started as energy in the sun. Whether it's oil or the energy in you or in plants or in animals, whatever, it started as radiation that came from the sun. The interesting part is we know that this light interacts with objects. It interacts with the fact that you can see this screen at all tells us that the light coming off this screen hits your eyes as a particle so that your body can process that light. If it didn't interact with these objects, you couldn't see them. You can see straight through the air effectively because there's nothing for the light to interact with in the air. Whereas when it hits the table, you can see the table. The light is interacting with it as if it were a particle. The light itself was a particle. So we have this weird combination where light is both a wave and a particle depending on what it needs to be doing at the time. When light is acting like a particle, we give it a particular name, a photon. This photon is a particle of light with no mass. That's really important. It is light with no mass that carries energy. Way back when we started talking about classification of matter, we said in order for it to be matter, it has to take up space and it has to have mass. We said basically everything that you could think of is matter except for light, except for energy, because energy has no mass, which is good because otherwise the light bulb hitting you with energy would hit you with actual physical tangible mass all the time. That would essentially be painful, but does carry some energy with it. We call that specific amount of energy a quantum or a quanta. A quanta is how we identify exactly how far electrons fall when they fall from various energy levels. When they fall from 3 to 4, they release a particular quanta of light. When it falls from 3 to 2, it releases another different, distinct amount of energy, a particular quanta. So these orbitals that are specific distances from each other always release very specific and consistent amounts of energy. Remember, how these electrons fall, that's how we identify different elements, but all of these different energy levels do fall different amounts. So therefore they fall with and release different amounts of energy. That's really all you have to understand with the dual nature of light. Understand what a photon is. Understand that light can be both a particle and a wave. We've done experiments to prove it, and we're more than happy to tell you in more detail about that in class if you want to come hear about it. But as far as the video is concerned, that's all you need to know. Make sure you get your practice done for wave theory. Work those math problems. Make sure you're able to do the algebra, and make sure you're watching your units.